Hi folks, we're going to take a look at this question from the Unit 4, Lesson 4 homework. So they're asking us to determine a model that we could use to determine the largest isosceles triangle by area that can be inscribed inside a circle of radius 1. Okay, now here technically they're just asking us for the model, so that would include the equation and the domain, but I'm actually going to solve the whole problem because we're going to see it's quite similar to the one we solved with a cylinder in a sphere. All right, so let me start by drawing a diagram. So let's draw a circle here. So we've got a circle, and then we're inscribing in that a triangle. And it's an isosceles triangle, so these two sides are the same. And the only concrete information we're given is that the circle has a radius of 1. So hopefully we're going to be able to use this information to help us solve the problem. So first of all, if I'm looking for the area of a triangle, I know I'm going to be working with the base times height divided by 2, or 1/2 base times height. And this equation, of course, has the problem we see very often, is that it's given in terms of two variables. Okay, so hopefully knowing that it's inscribed in a circle of radius 1 will be helpful. So the trick we've seen here is when we have a question that involves two different shapes, is find a way to connect them. And the way I'm going to do that is by drawing my radius in a particular way. I'm going to draw it so that it hits the edge of the circle right where the triangle touches the circle. Okay, and here, as we've seen before, is we can create a right angle triangle. Now, why is this useful? Because if I call this, say, x, this side of the right angle triangle, well, the base is just going to be equal to 2x. All right. Now, there's another good place to draw my my radius, is to draw it to the top, because I know that this is equal to 1 and this is also equal to 1. So if I say call this value y, I know that the height is just going to be equal to y plus 1. All right. So here I can either write x in terms of y or y in terms of x, because I actually don't want these two variables in here. So I guess I would, I'm just trying to see if either one of them looks like a nicer one to do. So if I do y in terms of x, I'm going to have a square root then plus 1, whereas if I do x in terms of y, I think in the end it's going to be about the same. All right, so let's do y in terms of x. So here I have y is equal to, so 1 is the hypotenuse, so the square root of 1 minus x squared. All right. And so now my height is just equal to square root of 1 minus x squared plus 1. All right, and so now I can input these into my equation. Okay, so 1/2, the base is just equal to 2x, so that works out nicely. And then the height is just square root of 1 minus x squared, and then plus 1. All right, and so let's see if we can figure out what the domain is for this function. Well, here, remember, x represents this value here. So what do I know? Well, I know it's definitely going to be less than, sorry, it's going to be greater than 0, because it's a measure of length. And you see that it's getting, the more I go, the further up I go along the circle, at most it can be equal to 1, the radius. Okay, in fact, it can't actually be equal to 1, because then I would just create a straight line. There wouldn't actually be a triangle that I'd be working with. So it has to be strictly less than 1. So here we have that 0 is less than x is less than 1. All right, and of course we know that because it's an open interval, I'm going to have to justify any optimal values. All right, so let's clean this up here. So I've got a is equal to x times, I guess I can, yeah, I might as well just distribute this here, x times square root of 1 minus x squared, and then plus x. And now I can take the derivative. Now, here I'm going to have to use the product rule for that first derivative, and the next one will be pretty easy. So let's solve this here. So derivative of the first is just 1 times the second function, 1 minus x squared, then plus the first function x times the derivative of the second function. So this is 1 minus x squared to the 1/2. So it's just going to be 1/2 times 1 minus x squared to the negative 1/2, and then times the derivative of 1 minus x squared, which is negative 2x. All right, and then finally plus the derivative of x, which is just 1. Okay, so I want to set this derivative equal to 0, and let's clean it up and then see how we can simplify this expression. So first of all, I see that that 2 is going to cancel out with the 2 in the numerator. So I've got the square root of 1 minus x squared. Then here, what are we left with in the numerator? We'll have an x times another x, okay? And I now have a subtraction, so minus x squared, and then this whole thing is going to go into the denominator. So square root of 1 minus x squared, and then finally plus 1. Okay? So now we have to solve this here, and while it's not technically a rational equation, because this is not a polynomial expression, we can solve it that way. Let's multiply both sides by the lowest common denominator. It's going to be nice because I've got 0 on this side, so I'm going to multiply both sides by root 1 minus x squared. So I've still got 0 on the left-hand side. Root 1 minus x squared times root 1 minus x squared is just going to be 1 minus x squared, so that's nice. Minus, it's already in that denominator, so that one's not going to change, and then plus square root of 1 minus x squared. Okay, so let's clean this up. So 1 minus 2x squared, and then plus square root of 1 minus x squared. So now we're starting to see that, why I gave that little hint there. So the derivative is taking a little work to work with. So let's just keep going here. So the question is how am I going to solve this equation? Well, I think what I'm going to have to do is bring everything to the other side that doesn't have a square root, and then I can square both sides to eliminate the square root. Okay, so here we've got, let's bring that to the other side. So we have 2x squared minus 1 equals square root of 1 minus x squared. And now I'm just going to square both sides. Okay. So this here, let's be careful. So we're going to square the first, so that's going to be 4x to the 4th, and then square the last. We'll write that down later on. Twice the product of first and last, so negative 1 times 2x squared times 2, so minus 4x squared, and then plus 1. And then on the other side, what do we have? Just 1 minus x squared. So now let's bring everything to one side of the equation. So here we're going to have 4x to the 4, and then negative 4x squared plus x squared, so minus 3x squared. Oh, and there's something very nice. That's going to make this equation very easy to solve because the ones just cancel out. So I'm just left with equal to 0. All right, so now this is fairly easy to solve. I'll start by factoring out the x squared. So I'm left with 4x squared minus 3 equals 0. So that means x can be equal to 0, which I'm not going to include because it's not part of my domain. Okay, and then I have x is equal to the positive or negative square root of 3 over 4. And of course, I'm not going to pick the negative square root of root 3 over 4 because x is a measure of length. And so what we have here is, and I'm just going to calculate it. I'm going to try to keep this exact if I can. It's not too difficult to do so. But I just want to make sure that this is in my domain, and I can see already that it's going to be because the square root of 3/4 will be between 0 and 1. But let's just get an idea of what it is since we're going to have to maybe do some work with it. So 3 divided by 4. So it's about 0.87. Okay, so definitely in our domain. So we just want to show that this x value of 0.87 gives us the largest triangle by area. All right. So let's take our area formula, or the derivative, and here I'm just interested from 0 to 1. So we have 0.87. So let's pick 0.01 and say 0.9, and let's stick this into the equation of the derivative. Okay, and I'll take this simplified form here. Okay, so let's just be really careful in doing this. So we've got 1 minus 0.1 squared. Okay, and then we'll take the square root of that, so exponent 0.5. Okay, and then minus, okay, so minus, what do we have? We have 0.1 squared divided by, and then we've got square root again, so 1 minus 0.1 squared, all to the exponent 1/2. Okay, and then here, let me just make sure that I did divide it. Yeah, I see the division there, so I want to make sure I don't make any silly mistakes. Okay, and then we've got plus 1. Okay, and that gives us something positive. And now let's do the same thing with 0.9. Okay, so 1 minus 0.9 squared. Okay, all square rooted. Okay, and then minus 0.9 squared. Okay, divided by, and we'll put 1 minus 0.9 squared, brackets to the exponent of 1/2. Okay, and then finally plus 1, and we have something negative. Okay, now because this is the only critical point in the interval, okay, and we have the increasing and decreasing behavior, so we have a local max at 0.87, or a square root of 3/4. All right, and so in this interval, it's continually increasing up to that local max and then continually decreasing for the rest of the interval. So this, in fact, represents an absolute maximum. Okay, so now here, again, they were just asking for a model, but I suppose what we can do is let's give the dimensions, okay, just for the fun of it. Okay, they could have also been asking for the actual area, but let's give the dimensions. Okay, so we have our base is just 2 times our x value, so just 2 times square root of 3/4 units. And then our height is going to be equal to, okay, so we remember it's this here, so 1 minus square root of 3/4 squared is just 3/4, and then plus 1. Okay, so that's going to be equal to, this is 1/4, so square root of 1/4 plus 1. Okay, if we want it to be really precise, we could even do some more simplifying, because the base is equal to 2 times, and this can be written as √3/2, since square root of 4 is 2, and that cancels out, so it even gets simpler. And similarly here, the height is just 1/√2 plus 1, and you can leave it like that, or you can add these two together. All right. So in the end, a fairly complex derivative, but this is where being careful really helped, that we didn't make any silly mistakes, and we ended up with an equation that we could solve relatively easily. But I just want to come back and recap how we came up with our model. Okay, again, always a good diagram is useful. And the idea here was to connect this triangle to the radius of the circle. And the way to do that is to draw those radii where the radius meets the intersection of the triangle and the circle. Okay, that's it for this one.